Hello, my name is Shakir Adas. Today I will be presenting the Statistics Engineering project. This presentation explores hourly electricity generation and consumption data for Turkey over the period of 2020 to 2022. Using statistical methods and R, the analysis investigates trends, patterns, and factors influencing energy use. The core objective was to provide meaningful insights into how electricity is consumed and produced in Turkey, which has important implications for planning and policy. The dataset used is substantial, over 26,000 hourly records covering various energy sources. The goal is not just to understand electricity usage, but also to support decision making through data-driven conclusions. This presentation has been developed as part of an academic assessment but offers practical insights for energy stockholders as well. And now understanding electricity demand is crucial in the context of rising energy needs from growing populations and industries. Stable electricity supply depends on understanding when and how energy is consumed. As countries transition toward renewable energy, detailed consumption insights become vital for integration and grid reliability. In Turkey, economic and climatic factors are reshaping the national energy mix. This study helps navigate those changes by analyzing past data to inform future decisions. Using data science tools, it connects quantitative methods with real-world energy challenges. The outcomes provide a base for smarter infrastructure planning and resource allocation in the face of increasing demand and climatic goals. The guiding research question is, what are the main factors affecting electricity consumption in Turkey, and how can this support better planning and forecasting? To address this, the study applied time series analysis, visualization, and statistical tests. It examined how energy use varies by hour and day and season, and how it's affected by different sources of generation. These insights can support more responsive electricity planning and help build forecasting models for future use. Understanding these factors not only improves operational efficiency but also contributes to national energy strategies and long-term sustainability goals. The dataset included hourly electricity data featuring variables such as natural gas, wind, solar, hydro, and total demand. Pre-processing involved converting timestamps into components like hour, month, and season to allow temporal analysis. Data cleaning steps included handling missing values using a method known as last observation carried forward and ensuring numeric consistency across columns. This structured the data effectively for visualization and statistical modeling. These steps were necessary to make the dataset analysis ready and to extract meaningful insights on demand patterns and generation source across different time frames. The average electricity consumption was around 35,800 per hour, slightly higher than average generation. Peak demand was observed during daytime hours, especially between 6 a.m. and 6 p.m., which reflects human activity cycles. Seasonal patterns were also evident, with summer months showing increased usage likely due to cooling systems. Visual tools like histograms and box plots showed a near normal distribution with some variability. Among generation sources, wind and solar displayed higher variability compared to more consistent sources like gas. These early observations provided a strong foundation for deeper statistical analysis. Demand was mostly concentrated between 28,000 and 42,000 per hour. This was confirmed through frequency tables and stem and leaf plots, which showed tight clustering around the mean. Quarter analysis further revealed that 75% of the data was under 40,084. Outliers were identified through box plots, through no extreme values disrupt the distribution. One key insight was the hydroelectric power showed a coefficient of variation over 50%, indicating high unpredictability. Overall, the relatively stable demand patterns support the use of parametric models and further analysis, reinforcing statistical validity. Confidence intervals and hypothesis testing. Statistical inference showed that strong reliability in estimating consumption patterns. A 95% confidence interval for average demand was narrowly set between 35,726 and 35,869, with a low margin of error due to the large dataset. Hypothesis testing confirmed that the true average demand is significantly greater than a baseline value of 35,000. Seasonal t-test revealed thus that summer consumption is substantially higher than winter by approximately 1,750. However, only about 7.6% of the hours saw renewable sources overtaking non-renewable, emphasizing the dominance of fossil fuels in the supply chain despite ongoing energy transitions. When comparing energy sources, natural gas emerged as the dominant contributor, averaging 9401, while wind averaged just 3420. Variance tests showed that daytime demand fluctuated significantly more than nighttime demand, likely reflecting business and social activity. A paired t-test confirmed that generation was consistently lower than consumption by around 941. This shortfall points to the importance of imports or energy storage system. Seasonal variations in the wind and solar were also statistically confirmed, emphasizing the need to manage renewable more dynamically across different months. Correlation and regression. Correlation analysis showed that natural gas had the strongest positive relationship with demand. A regression model using 4 energy sources, gas, hydro, solar, and wind, explained 88.6% of the variance in electricity consumption, highlighting the effectiveness of these predictors. Each source was statistically significant, and residual analysis confirmed that the model assumptions held well. The model generated tight prediction intervals, suggesting high forecasting accuracy. This registration framework demonstrates how past generation data can be reliably used to estimate future demand, aiding in the load forecasting and resource allocation. T-square tests revealed that energy generation was not uniformly distributed across sources, with natural gas and coal being disproportionately dominant. Analysis also showed that solar generation is highly dependent on the time of the day, confirming its diurnal nature. ANOVA tests identified significant differences in the consumption across seasons, with summer showing the highest mean demand. Post hoc tests like Turkey's further broke down these seasonal differences. A two-way ANOVA also found interaction effects between season and time of day on natural gas usage, demonstrating how generation pattern depends on both short and long-term cycles. Non-parametric tests. Non-parametric methods provided further confirmation of earlier findings without relying on normal distribution assumptions. The Wilkes-Cohn test reinforced that generation was consistently below consumption. The Mann-Whitney U-test highlighted seasonal difference in wind power, while the Croxall-Wallace test did the same for solar energy. Spearman's rank correlation found only a weak positive relationship between wind and demand. These tests support the robustness of the findings and help ensure that results are not artifacts of specific statistical assumptions. They add an additional layer of validation for key trend observed in the study. Interpretation and implications. The analysis revealed that Turkey's electricity demand is generally predictable and shows consistent daily and seasonal patterns. However, consumption regularly exceeds generation, suggesting a need for improved balancing through import, storage, or generation increases. Fossil fuels continue to dominate the supply while renewables are underutilized. The regression model's high accuracy makes it suitable for short-term forecasting. Seasonal and hourly effects on both demand and generation have practical implications for grid management. These insights can help inform energy policies, partially those targeting efficiency, sustainability, and renewable integration. Conclusion and future directions. The study confirms that electricity demand in Turkey is shaped by predictable temporal and source-based factors. The grid still depends heavily on fossil fuels, leaving room for better integration of renewables. Predictive models based on historical data can be developed for more accurate real-time management. Policymakers must consider variability across seasons and hours to ensure resilience. Future work could incorporate economic and weather data as well as explore battery storage and international grid connections. Expanding the analysis to include neighboring countries could also support broader regional energy cooperation and planning. Thank you so much. This was our project for the statistics of engineering.